What's going on, guys? Gerson here back again. Today I learned sobre exercise 1C.1 or the biochemical principles. So let's get started. First by letter A. The letter A is practically equals to letter B. So we both in general, but I'll focus on the letter A. So the problem requires you to determine the energy transition between one quantum level to another in a box. So let's get started again. The transition is between the level n plus 1 to the level n plus 1, which is 5, and n, which is 4. We need to know that the energy emitted is the variation of energy, which is the energy of the state n plus 1 and minus the energy of the level n. We know the variation of energy is equals to height and Ni, in which height is the Planck constant and Ni is the frequency. But we know that Ni is equals to C over wavelength. And we need to know also the formula to the energy in a quantum level and in a particle in a box. The energy of a particle in a box is equals to n square height square over 8 ml square. And the energy na sublevel n plus 1 equals n plus 1 square height square over 8 ml square. We know that n equals 4, so we place 4 here, and we get 16 height square over 8 ml square. And here we get 5 square height square 8 ml square, which is equals to 25 L square over 8 ml square. M is the mass of electron, L is the size of the box, and H is the Planck constant. So we subtract the level of the higher energy to the level of lower energy. So we get 25 H square over 8 ml square minus 16 H square over 8 ml square. This yields 9 square H square over 8 ml square. And we equals this to height over. So we need to know the wavelength, which is lambda. We cut Planck constant from one side and one from the other side, resting one, and we get C over lambda equals 9 height over 8 ml square. And lambda that we want to know, rearrange this, we get 8 ml square over 9 height times C. So that's the equation that we will place we'll substitute the values for M, L, and C and H. So I'll open another page here. We knew that the wavelength is equals to 8 ml square over 9 H times C. We need to substitute here the 8 the m, which is 9.1 times 10 to the negative 31 kilograms, times the size of the box, which is 1.1 times 10 to the negative 10 meters. That's square times the speed of light in a vacuum, which is approximately 3 times 10 to the 8 power meters per second. Everything over 9 times Planck constant, which is 6.63 times 10 to the negative 34 joules second. We must recognize that 1 joule equals 1 kilogram meter square per second square. So when we solve this, gives that is equal to approximately 8. Let me put here, I shift the Portuguese notation from English notation. The English notation from Portuguese notation is equals to this meters. The units cancel, so it rests lambda equals 8.24 times 10 to the negative 9 meters, which is equals to 8.24 nanometers. That's the answer for letter A. And now we go to letter B. The unique difference from letter B to A is that the sublevel n plus 1 is equals to 4 and n equals to 3. So the delta E, the variation energy, equals energy of n plus 1 minus energy of n, which is 4 square h square over 8 ml square minus 3 square h square over 8 ml square, and this equals to 7h square over 8 ml square. But the variation of energy is equals to h(e), but h(e), as we saw, is equals to hc over lambda, and this is equals this. So we need to solve lambda, rearranging and canceling this by one of these. We find that lambda is equals to this expression after rearranging. And placing the things, we know m, which is the mass of the electron, as the first letter, and the L is the same size of the box, C is the same, and H is the same. After placing each value here, we find that this yields 10.6 nanometers. That's a energy lower than the first one, because the wavelength is larger. So that was the exercise for today. I hope that you found this helpful. I hope that you like it. And so if you do, subscribe to the channel and like the video. And thank you, and see you next time.